All right, today we're going to pull back the curtain on one of the coolest data structures out there, the binary heap. Seriously, if you've ever wondered how to build a super fast system for managing priorities, like what task a CPU should do next or who's at the top of a gaming leaderboard, then you are in for a treat. Let's get right into it.
So, let's kick things off with a classic challenge. Picture this. You've got this huge, messy collection of items, and it's changing all the time. People are adding stuff, taking stuff away, and your one job, your only job, is to find the smallest item, or maybe the highest priority item, instantly, at any moment. How on earth do you do that without grinding the whole system to a halt? Well, that is the exact problem the binary heap was born to solve.
So what is this thing, this binary heap? Well, at its heart, it's the powerhouse, the engine, that makes something called a priority queue work, and it makes it incredibly fast. Okay, if we get a little formal for a second, the textbook definition is a complete binary tree that also satisfies the heap order property. Now, don't let the jargon scare you. Those two phrases, that's the whole secret sauce. The complete binary tree part is all about speed, and the heap order property is all about staying organized. Let's break down what those actually mean in plain English.
So here are the two golden rules. First up, the complete tree rule. All this means is that we fill the tree up from left to right, top to bottom. No gaps allowed. You fill one level completely before you even think about starting the next. And why is this so important? Because it guarantees the tree stays short and bushy, not tall and stringy. This keeps its height at what we call O of log n, which is just a fancy way of saying it's super shallow and fast to navigate. Rule number 2 is the heap order property. For a min heap, which is what we'll be looking at, it's simple. Every parent has to be smaller than its own kids. That's it. And the beautiful consequence of this? The smallest item in the entire collection is always, and I mean always, sitting right at the very top, just waiting for you.
And here's where things get really clever. You'd think we need all sorts of complicated pointers to manage this tree structure, right? Nope. A binary heap is actually just a concept that we map perfectly onto a simple array. That's it. And we can navigate this tree inside the array using these 3 simple math formulas. With these, you can instantly find the parent or children of any node. It's like a magic trick. This means no extra memory for pointers, which makes heaps ridiculously efficient and fast.
Okay, so how do we actually add something to this heap? Let's talk about our first major operation, insertion. The best way to think about this is to imagine your new value is a super light balloon. What happens when you let go of a balloon? It rises. That's exactly what we're going to do here.
This whole process is called sift up, and it's actually pretty straightforward. Step 1, just stick the new element in the first open spot. In our array, that's always at the very end. But wait, that might have just broken our heap rule, right? No problem, we fix it. Step 2, we look at our new element and compare it to its parent. Is it smaller? If yes, we swap them, and then we just do it again. We keep comparing and swapping our way up the tree, letting our little balloon rise until it either finds a parent that's smaller than it is, or it reaches the very top and becomes the new root. The heap is happy again.
And because we're only ever traveling up the height of our nice, short tree, this operation is ridiculously fast. Think about it. Even if your heap has 1,000,000 items, you're only going to have to do, maybe 20 swaps tops? That's incredible. And that's why we say insertion has a time complexity of O log n. It scales beautifully.
All right, so adding stuff is fast. What about taking the most important thing out? That minimum value at the top. Well, this is basically the opposite process. If insertion was a light balloon rising, deletion is like a heavy box sinking down to find its rightful place.
See, we can't just yank out the root and leave a big hole at the top. That would break everything. So we do another clever little trick. We take the root and we swap it with the very last element in the heap. Now, the minimum value we wanted is safely at the end of the array, and we can just pop it off. Easy. But, now we have a problem at the top. The element we just put there is probably way too big, so we have to fix it. We take this new root and we compare it to its children. And this is key. We swap it with the smaller of its 2 kids. Then we just keep doing that, letting our heavy box sink down level by level until it finally settles in a spot where it's smaller than both of its children. And just like that, the heap property is restored.
And you guessed it, just like our balloon going up, this box is only sinking down the height of the tree. So deleting the minimum is also a super efficient O of log n operation. Fast in, fast out.
Okay, so we know how to insert things one by one. That's cool. But what if you're handed a big, unsorted pile of data, a whole array, and you need to turn it into a heap? Is there a better way than just inserting every single item one after another? The answer is a huge yes. And honestly, it's one of my favorite tricks in all of computer science.
Now, logically, you're probably thinking, okay, I have n items, insertion takes O log n. So I'll just do that n times. The total time must be n times log n, right? O(n) log n. And you know what? That's a totally logical, perfectly reasonable assumption, and it is completely wrong. And here's the big surprise. You can actually build an entire heap from scratch in linear time. That's just O of n. This isn't some small improvement, it's a massive optimization. And it's a classic question in coding interviews. So how on earth is this possible?
The secret is to build the heap backwards, from the bottom up. Think about it. The entire bottom level of the tree, the leaves, they don't have any children, so they're already perfect little heaps. That's about half our nodes, and we don't have to do any work on them at all. So we start from the last node that actually has kids, and we perform a sift down on it. Then we move back one and do it again, and again, all the way to the root. Look at the numbers here. Most of the nodes are near the bottom, so they only have to sift down 1 or 2 levels. It's only that single node at the very top that might have to do the full log n amount of work. When you add it all up, it turns out the total number of swaps is actually less than n. It's a bit of mathematical magic that gives us that amazing linear time build.
And this brilliant bottom-up method comes to us from an algorithm by Robert W. Floyd way back in 1964. The core genius of it is this. Because you're starting from the bottom, you guarantee that by the time you get to any given node, the little subtrees beneath it have already been fixed. They're already perfect heaps. So you're just fixing one level at a time on your way to the top.
So why does any of this matter? Why have we gone through all this trouble? Because heaps are your secret weapon, especially when you're staring down a tricky problem in a coding interview that's all about priorities.
Let's put the binary heap head-to-head with some other options. You could use a sorted array, right? Finding the smallest thing is instant, O of 1. But try adding something new, you have to shift everything over. That's slow. What about a balanced binary search tree? Inserts and deletes are fast, O of log n. But just to find the minimum, you have to traverse all the way down the left side, also O of log n. The binary heap, though, it hits that perfect sweet spot. You can peek at the minimum in O of 1 time. It's right there at the top. And your inserts and deletes are still that super fast O of log n. For priority queues, it's simply the best tool for the job.
And trust me, once you know what they are, you start seeing heaps everywhere. They're working behind the scenes in your computer's operating system, deciding which program gets to run next. They're at the core of algorithms like Dijkstra's, which finds the shortest path for your GPS. And they are the classic go-to answer for that famous interview question, how do you find the top K items from a massive, endless stream of data?
Okay, so let's boil it all down. Here's your interview checklist. First, know those parent-child formulas like the back of your hand. Second, when you're writing that sift down function, please remember to compare both children to find the smaller one before you swap. That's a super common mistake. Third, be ready to explain exactly why the heap build is O of n. That'll really impress them. And a little practical tip, if you're using Python, the heap queue module is a min heap. If you need a max heap, just push the negative of your numbers onto it. It's a clever little hack.
All right, I'll leave you with one final thought puzzle to chew on. Imagine you're working at a social media company, and you have a fire hose of real-time text data flying by. How would you design a system to always know the 100 most frequent words being used right now? The solution is elegant, efficient, and uses exactly what we've just talked about. Give it some thought. The answer is pretty cool. Thanks for watching, and happy coding.